All right, now for real. I'm very happy to be able to introduce Shou-de Lin. Shou-de is an alum of ISI who graduated here about 10, 12 years ago. Been a long time. He originally came from University of Michigan, already with a master's degree, then worked for Craig Knobloch for a while, and then mysteriously found his way to me as an advisor. And I, at the time, worked for a link discovery, sort of a new area people were interested in, motivated by counterterrorism. And they said, well, we want to find these things, but we don't know exactly what we're looking for. And so that kind of spawned this whole area that he then later made his dissertation in finding interesting, abnormal nodes in large semantic graphs and characterizing them, explaining them. Shou-de was always very sort of prolific and worked very hard, so that wasn't enough for him. So he also worked, he found Kevin, worked with Kevin on some very cool stuff in natural language, on deciphering ancient manuscripts, and also then got a master's degree from the linguistics department at USC. So he was sort of very broad in his interests, and he sort of kept going like that. He always was sort of at the intersection of machine learning, data science, knowledge discovery, and natural language. And so after graduating, he moved back to his home country, Taiwan, and started a position at National Taiwan University. And he already, when he was here, he placed once in the KDD Cup. So KDD is this, premier knowledge discovery conference. They have an annual challenge prize. And if any of you have ever looked at that, these are hard to just compete in, let alone to win. So he, as a student already, he placed, I think, second in 2003, and then it sort of became an obsession. And so with his students and TU, he, I think, won the KDD Cup 5 times. So winning it just once would be an incredible achievement, but he's actually done it 5 times, and now they don't let him play anymore. And so he's continuing in that area, in this intersection of research fields, and today he will tell us about graph and knowledge embedding.
Thank you, Hans. Very happy to be here, and so I was here like 12 years ago as a student, and so very happy to see our old friends, Jose Luis and Hans. Also, like Nayin was my visiting student, I think 4 or 5 years ago in NTU, and so it's good like she got into this really excellent place to like keep her career and in NLP. And so today I'm going to talk about actually what people believe to be it's named a graph embedding or knowledge embedding, which is kind of a continuity of what I have been working on in my thesis. It's how to analyze a huge graph and huge network. And so a brief introduction of my lab here. So I'm leading the machine discovery and social network mining lab in NTU, and so our focus is trying to do some sort of learning or discovery from big data, large amount of data, and be it a social network or natural language or Internet of Things. And so we have been working on all those areas, and we are trying to tackle some practical issues for learning. And so before I actually go into the focus of today's talk, I want to introduce the other direction of my team, which is I have been actually very interested in answering a question, can machine discover? So we already know that machine can learn well, but can machine actually do better than learning as trying to discover things? So we have been working on this, including one of the previous projects with Kevin on decipherment. And we work on machine creation, try to use machine to write Chinese, to create Chinese classic poets. And we also have a recent work on the lyric, Chinese lyric writing from machine. And we also try to see if machine can serve the role of a detective. And my PhD thesis is all about finding abnormal instances in the graph. And so later on, we work on some sort of interesting topic in this direction, including finding novel topic diffusion in text. Also discover unseen links between people. and also finding the hidden relationship between people in the regular network data. And so that's what we have been doing. And in recent years, we are trying to see if there is a way, general mechanism that allows us to improve a general supervised learning performance through unsupervised discovery. And we have a bunch of recent works on this direction. Okay, then I move on to today's talk. So actually, this is kind of a survey work. So we are trying to overview what's going on in graph embedding and knowledge embedding. And I will introduce one of the recent work of us on this direction. And then I will describe what I believe to be the next. First, graph embedding. Some people call it network embedding. So it's the goal of trying to represent the node in a network using a vector. Okay, so it's a vector representation of entities in a graph. Okay, so why do we want to do that? Because we know how to deal with vectors better. So if we have vectors, all kinds of machine learning, data mining, clustering, classification, all those algorithms, we can deal with vectors. And so that's why we want to represent things as a vector. Also, and so the key idea lies in two main concepts. To do this kind of embedding, we want to ask first what to preserve, and the second is how to preserve. And so it's, although there are like tons of papers working on this direction, but all of them they are trying to answer this kind of question. Okay, and so we also, some people consider some auxiliary information from the graph, but basically that's the two key questions to ask. And the other area I will highlight in this talk is what people call knowledge embedding. So it's a bit different from graph embedding, because in knowledge embedding, people cares more about the relationship between entities. Okay, for example, wheel is part of car, and shoulder is has an affiliation of NTU. So in those knowledge couple relation is very important. So in knowledge embedding, people care about not only provide an embedding for nodes or entities, but also for the relations. Okay, and it's interesting to learn that these two areas, although they kind of dealing with graph, but they are not really overlapped. So most of our people in KDD are working on graph embedding, and people in NLP focus more on knowledge embedding, and they even have two different survey papers on these two different areas. Okay, and I will start with graph embedding, and also eventually I will introduce one of our recent work in this area. Okay, and a lot of different mentions on this topic. They are all about the same thing. Okay, so people use graph factorization, social representation, network embedding, graph representation, feature learning, graph embedding, network representation. All those papers are talking about the same thing. So here we generally call it graph embedding. As I mentioned, we want to answer these questions. First, what do we want to preserve in the embedding? And then how to preserve those we want to preserve. And eventually, we care about the application for this kind of technique. Okay, so one by one, first I will talk about what to preserve. And the common goal for most of the works, they try to preserve the so-called proximity information in a graph, meaning that two nodes are closer to each other in a graph should share similar embeddings. Okay, so but different papers, they have different definition of this similarity. Okay, so they define similarity differently, but the underlying assumption is the same. And another advanced goal, what I call meta proximity, is to actually represent it as a community. Okay, so they want two nodes that they are believed to be in the same community in the graph should share the same or similar embeddings. But basically, these two ideas try to capture the proximity information in the graph. And how do we do that? So here I introduce a general framework. So most of papers I will introduce later on actually follow this framework. So people like to model it as an optimization task. Okay, so what do I mean by that? So in an optimization task, we want to adjust those embeddings so that some sort of objective function can be optimized. Okay, and so then what kind of information do we have in a graph? So normally people consider the connection between nodes. That's most apparent information in the graph. Okay, so in this optimization task, we first build a what we call positive set. So those positive set contains of pairs of connected nodes or pairs of nodes people believe to be very similar. And in this sense, we want their embedding to be similar. So their similarity to be as high as possible. And there's another set people, so we name it as a negative set. In the negative set, we want those disconnected nodes or those nodes by certain measure we believe to be distant to have very different embedding. Okay, so those are the basic chaining sets we have. We have these two chaining sets, and we want to train an optimization model that adjusts this embedding to optimize the similarity of nodes between in the positive set and minimize the similarity in the negative set. Okay, and so different models usually consider different kinds of measurements for proximity. And for example, one trivial way to do similarity is to do the inner product of these two vectors. Okay, so a general framework looks like this. So we have a positive instance H, we have a negative instance L, and we want to train these embeddings to optimize this H and L. And so one thing to be aware is that for negative instances, usually the complexity is high because you have n squared, the minus H. So it's generally people are not using all n squared negative instances as training. So they subsample only a subset of it. And commonly, people first build what we call similarity matrix, and they try to adjust the embedding to match this similarity matrix. So this similarity matrix is an n by n matrix. N is the number of total nodes in a graph. Okay, and the value in this matrix is the similarity defined by whatever measure people care. And so one particular way to do that is to use a Pth order proximity. Okay, so this P means like the distance we really care. So the first order means they are directly connected. The second order means they are connected by one neighbor. The third order means they have two neighbors between connection. Okay, and so different algorithms can try to preserve different order of proximity in their algorithm. Okay, and so here is an example. We can formulate this embedding generation as a classification task. So for classification task, you have this f function. So this f function takes the similarity between two nodes and generates a probability. So you can use sigmoid or softmax. And so the probability of this positive set should be as high as possible, and the probability of the so the probability of the negative set should be close to 0. So by optimizing, finding a U, which is the embedding of the nodes, to maximize this, we can formulate it as a classification task and apply all kinds of classification algorithms on it. And you can also model it as a regression test. So recall that we have this similarity matrix capture the similarity between nodes, and so we want to make sure the inner product of these two, the source and target nodes. Okay. And the inner product of the source and target nodes actually can match the score in the similarity matrix. Okay, or people use KO divergence. Okay, so then I will go into detail to show how people in general solve this application task. So there are actually 3 different categories. And the first one I'd like to introduce is the most common one. So people are use SVD or matrix factorization based model to solve this problem. So recall that we have this graph relevant matrix, that S over here I'm using A. And so with that similarity matrix, we can generate a low rank decomposition of the 2 smaller one, U and V. And U transpose V will be equivalent or will be as close to the similarity matrix as possible. So by doing that, we actually, doing the factorization, we actually create a set of embedding for all the nodes. And let's present it as U here. And so we found that at least there are 3 papers and they are doing this using SVD type of solution. And the difference between them is there are different ways to generate this relevant matrix A. Okay, for example, in this graph representation, they are trying to preserve, my memory is correct, the first order, second order, and third order proximity. And so using the combination of these 3 proximity, they can generate this graph matrix A, and then they decompose it into U and V, and eventually that U becomes the embedding. And the second type of solution, what we call random walk-based models. So the random walk-based model try to reduce this problem into a word embedding problem. I suppose people working on NLP are very familiar with word embedding. Once you have a sequence of words and you can use one to predict each other and like skip grant. And so while trying to, the generation of the embedding would be equivalent to finding a good latent representation of those words to predict the neighborhood structure. Okay, so here the idea is very simple. So we can perform random walk on the graph. So each time there's a random walk, then we generate a path. This path will look like just like a sequence of nodes. And so that's similar to the sequence of words as people doing the word embedding. And then eventually, if you do this random walk millions of times, you get millions of sentences or millions of paths, and then throw it to a word embedding algorithm, and then you generate a set of embeddings for those nodes. And so deep work, I think people are very familiar with this, and node-to-vector are 2 very famous algorithms in this category. And actually yesterday in Wisdom, so it's held over there in Reeds, there's an interesting paper describing that they have this very interesting finding that the 2 category of things I just introduced, they are essentially very similar. So they consider 4 different algorithms: deep walk, line, PDE, and node-to-vector, and they realized that those random walk-based algorithms actually try to do matrix factorization on certain type of matrix. And so in their conclusion, they realized that although it seems like random walk-based algorithm is very different from this factorization-based algorithm, but those random walk-based algorithms, they are trying to optimize, they are trying to do factorization on more complicated matrix. So all of them can be regarded as a matrix factorization-based method, but they have different ways to generate this matrix to be factorized. And the third type of solution is what people call deep neural network-based models. So because deep neural network is very popular here, so everybody wants to try it on every kind of task, and that's why people have this DNN or CNN-based embedding. Okay, and the basic idea is very simple. They are trying to use deep autoencoders. At least one set of solution is based on deep autoencoders. and I will introduce. I'll go back on the second part later, and I will introduce SDNE, Structured Deep Neural Network, to you as a representative in this category. Okay, so in SDNE, it tries to preserve the first and second order proximity, but they are doing it in a different way. So they are trying to use this deep neural network to capture the abstract meaning of instances. And what they did is the input to a neural network is an adjacency matrix of the graph. Okay, so the adjacency matrix means like if its neighbor is 1, if not, it's 0. So it's a binary vector. And they are using autoencoder, meaning that they want to reconstruct the input in the very end. So there's an encoding part, there's a decoding part, but eventually they want to reconstruct the input adjacency matrix. And so the embedding actually were derived as the middle here. Okay, so the encoding before decoding the code, then this is a more compact representation of the entity, and that becomes the target embedding to be learned. And that's the first equation. The first equation really actually capture this autoencoder, and they have this scalar b to actually downplay, because in a graph it's usually sparse, means that or in an adjacency matrix it's really sparse, means that a lot of zeros, relatively fewer ones, and so they have this scalar to highlight the importance of those 1 and downplay the weight for 0 to make sure it's not the learning will not go to the wrong direction. And they have this, so this actually capture the second order proximity, because the second order proximity means that if you capture the neighborhood, then you know what kind of neighborhood you are, and 2 nodes of similar neighborhood, they will have similar embedding, and that's what we believe to be a second order. And they also want to capture the first order proximity. So this is trivial. So this Y represents the embedding that's done in the middle layer. So they want to make sure if 2 nodes they are connected, then their embedding should be similar. Okay. So by use this L as the objective function to optimize in the deep neural network, they are allowed to generate a set of embeddings for those entities, and they satisfy both first order and second order proximity. And so the basic idea is try to use this deep neural network as a high level representation of whatever input you provide to it, and those high level representations you add some constraints like this first order proximity to really make sure it satisfies and whatever criteria you care about. And the last term is the regression term, just to make sure it doesn't overfit. And there's another interesting work I like to measure, is this called graph convolution network. So people probably already know that CNN has been a very effective algorithm in deep neural network, and people apply it to image and video. So these people, they want to apply CNN for graph embedding, but the very naive idea is like you have this adjacency matrix, so it's like a 2-dimensional graph of figure, right? And so you apply CNN on this 2-dimensional matrix, but it won't do you a very good job, because those in an adjacency matrix, those rows are interchangeable. Okay, but in a regular image, those rows are not interchangeable. So CNN wouldn't be able to capture this kind of information. So they are using this what we call the Laplacian graph. So they transform the original adjacency matrix into this Laplacian graph, and Laplacian graph has a lot of good property, like semi-definite, whatever. And so people are using this for like clustering, spatial clustering, and all kinds of things. Somebody ask question? Or?
No, should probably just tell the person to mute their phone.
Yeah.
Okay.
1, 2, 3, 5,
1,
0.
2, 3, 3, 5, 9, 0, 8, 6, 3, 5. Okay, good. Thanks. Okay. Oh, good. Good. Okay. And so that's how people apply the CN on a graph to get the embedding. So very interesting work. One particular drawback for this. So this one is learned supervisory, and means that you need some sort of label data. For example, the type of the graph, some sort of label data to learn it. But most of the other graph embedding algorithms, they are unsupervised, meaning that we don't need any extra label on the graph or on the node. What we need is the graph itself. Okay, the graph itself allows us to do the embedding. Okay, and there are other methods which I will skip. And why people care about embedding? So there are a lot of applications we can apply after getting the embedding. As I mentioned, classification. For example, like document classification. If we treat those documents as a website and they are connected, so you get a very huge graph, and you get every document embedded, and then it can be used for classification, and you can use for regression and community detection. For a big graph, you want to detect what kinds of community. So if we can have a vector representation for each node, then we can throw that into a clustering algorithm that will give you a set of a cluster as community. And people want to do link prediction, predict missing link in the graph, visualization, ranking. Later on, I will introduce our work. Let's focus on the ranking part of the application. And before that, I want to also introduce the other spectrum, what people believe to be a large embedding. And again, there are different names for this topic. So people are talking about modeling multi-relational data, large graph embedding, entity relationship embedding, type constraint representation, distributed representation. Those are talking about the same thing as a large embedding here. So what's the general framework for large embedding? So most of the works actually consider this score function. So as I mentioned, in large embedding, there are three important components: the source node, target node, and the relation between them. Okay, so we use IJR to represent these three. So given the embedding of these three entities, we can generate a score. And the idea is very simple. So we want all the observed relation to have high score, and the unobserved relation to have a low score. And so that's the basic idea. So in this case, we need a way to generate score from the embedding. It's called score function, and we need a way to generate an embedding. And eventually, we want to optimize this S. Sorry. A general objective function looks like this. So as I mentioned, so there are a bunch of probably tens of thousands or even millions of observed relations over there, and we want them to have as high score as possible. And also and people generally sample a bunch of negative instances here, and they want the negative instances to have low score. So it's again, it's like a maximum likelihood kind of optimization task. Then I will introduce some of the models in this direction. So most common one is the people call bilinearity based model. So in bilinearity model, people are generating the score by simply so this U is a vector, and so the UI represents the embedding for the source, and the UJ is the embedding for the target, and this R is a matrix, so it's an embedding for the relation. Okay, so this is a general formula. Okay, and different algorithms are different in how they define UR and how they model this. So for example, I think the general form is derived from this NTN, neural tensor layer paper. So they have some sort of constraints on the relation embedded, and different papers, they have different constraints on the how they represent the embedding for target and for source and for the relation. But eventually the multiplication of them becomes a score, and they want to maximize the score. It's a bilinearity based model. And another set of solution we call a translation based model. So in translation based model, I think probably people in NLP are familiar with this. So we learned that in word embedding there is a famous analogy, so it's like king and queen. So there's a vector for king and vector for queen, and the difference should be like gender. And so the difference between king and queen will be probably the same as the difference between boy and girl, something like that. Yeah. And so here is a similar idea. So we want the difference between the source and the target. So here we use H as a source, T as a target. So their difference will be captured by this relation R. And the very naive way is to represent this as a triangle. So we want the embedding of H plus the embedding of R will be as close to the embedding of the target node T. And there are a lot of variations from this trans E model. For example, this trans H, they have not as strict constraint as trans E. So in trans H, they don't require H plus R equals T, but they only require the some sort of transformation from H to another plane, and would be equivalent, plus R would be equivalent to the transformation from T to that plane. Okay, so in this case, it's like some function of H plus this embedding of R will be equivalent to some function of the target node U. Okay, so that's a general framework, and people have different ways to define those functions, to learn those functions. But in general, they are trying to satisfy this kind of connection between those entities. This is a good, nice review paper. They actually provide different score functions for different model. Okay, so they kind of cast this particular knowledge embedding problem into this score optimization test. And so different papers, they have different ways to define the score, and they have different ways to do the optimization, which means they have different ways to find a set of embeddings to optimize the score. But the basic idea is the same, just like you have this particular function, and this function probably satisfies some of the physical property of whatever you care about, and then you find a good optimization technique to find the embedding to optimize that score. Okay, so then I will introduce recent work. So we published a couple months ago in NIPS in graph embedding. Okay, so later on I will describe the experiment. So this probably give you some idea how people evaluate this kind of technique. So okay, again, so we want to ask first what kind of information we want to preserve in this embedding. And so first of all, we need to preserve proximity, just like everybody else. So we want similar nodes to have similar embedding. And in this paper, we actually introduce an additional goal. We want to preserve the ranking of the node, or the importance of the node. So why do we want to do that? So I suppose everybody knows PageRank. Okay, so if you a graph, then you run PageRank, then every node get a PageRank value. That value represents how important this node is in comparing to everybody else in the graph. So what does it mean? So PageRank is unsupervised. Given any graph, you can run the PageRank, get a PageRank value for every node, meaning that this ranking information seems to be intrinsic in a graph. For a graph, you should have the ranking for the nodes and then capture the importance of this node. So if this is intrinsic, why not we try to capture this kind of information in the embedding? So that's our basic idea. So we want the embedding to some extent capture the importance of the nodes, but not just the proximity information of the node. Okay, and so as I mentioned, there are different models. People use SVD, matrix factorization, random walk, deep neural network, and we are kind of lies in the deep neural network side. So we are using what people call SIMS neural network to perform optimization in this task. Okay, so SIMS neural network is a multitask. So there's a two string of neurons here. So it's usually used for multitask learning, in that you have several different goals and you want to satisfy those objectives at the same time. And so people are using this kind of network. And so why do we want to choose this? Because as I mentioned, we have two goals to satisfy. First is to make sure the proximity is preserved. Second one is to make sure the node ranking is preserved. Okay, and our input is a pair of nodes. A pair of nodes, and it's a generative model, meaning that we want to learn the embedding of U in red color here, and the generative model allows us to use U to generate whatever information we want to preserve, and eventually we want this embedding to generate first the ranking value of, or the PageRank value for that node. And second, we want to preserve the proximity. And in this framework, we kind of make a tricky, so we kind of discover interesting things. And preserving the proximity can be modeled as doing some sort of a community detection to make sure the right candidates are in the same group. So I'll talk about that later on. Okay, so for the proximity, recall that. So people are probably familiar with deep neural network. So in deep neural network, we are using backpropagation to train the weight of the nodes in the neural network. And usually there's an objective. So there's a label over there. So ground truth. So you use the ground truth to backpropagate the difference to the network. But in this kind of task, it's unsupervised. Okay, so we don't have this. We don't have a label for each node. So there is no way you can use that to train the model. But the goal here is to design some sort of objective function on top of the neural network, and then this becomes a optimization task. So we want to optimize this objective function. So whatever weight you are assigning right now, you can use this objective function to calculate the gradient and backpropagate the gradient to those nodes to adjust the weight. So that's the basic idea. And then the key will becomes how do we define or how do we design those objective function. And we want to design the objective function in a way that optimizing it allows us to preserve these two things we want to preserve. Okay, and so for proximity preservation, the idea is similar. So we want a linked entity to have a similar embedding, and non-connected nodes to have a different distance embedding. So this can be, as I mentioned, modeled as a general classification task. So there's a set of positive instance, and there's a set of negative instance, and we want to optimize the likelihood or log likelihood of the positive one and minimize the log likelihood of the negative one. And so that's a general solution. And one thing that's probably worth mentioning is that, so our way to produce the probability of this link is different from the traditional way of using, for example, using inner product. Here we are using what we call trifactorization. Trifactorization looks like this. So this is embedding for the source, and this is embedding for the target. And there is another matrix in between we want to learn. And why do we want this more complicated formula to generate this likelihood instead of using this basic matrix factorization as D transpose Z? There are several reasons to do that. First, and we actually show that by doing this, we can preserve the second order proximity, meaning that if you get there's a link between I and J, and there is a link between J and K, this formula guarantees we also get high score for I and K. So this allows you to preserve the second order proximity. Also, like this allows us to consider direct graph. Okay, so direct graph means there's a direction from the source to the target. If we are using this D transpose Z, so it's symmetric, meaning that it doesn't care if it's source to target or target to source. So this symmetric formula doesn't allow you to capture the direction information in the graph, but this trifactorization allows us to do that. So if we swap I and J, so the value will be different. Okay, so because there's a middle, there's another matrix to guide the direction here. Okay, and also we prove that to do this kind of trifactorization, we have some connection with maximizing the probability of nearby nodes in the same community. And the second term we want to preserve here is what we call node ranking. So the goal is to preserve the PageRank value for each node in the embedding. So how do we do that? So in our framework, so you can see that here there is a node ranking goal here, and we want eventually this embedding allows us through this deep neural network allows us to generate the PageRank value of it. Okay, so that's the goal. But how do we do that? And so we actually realize that by optimizing this formula, by putting this formula into the objective function, we can achieve this goal. And that's an interesting finding by somebody, I think a couple of years ago. They realized that normally people do PageRank using simulation. So you have this big graph, and then you simulate the flow of the PageRank is like pass your flow, like the amount of PageRank value to your neighborhood. So you do this kind of simulation a couple of times, several times, then you will saturate, converge to a steady point. That's the PageRank value. But from the optimization point of view, it's equivalent to optimize this particular equation. Okay, so optimizing this equation will allows you to eventually get a stable PageRank values for each node. But the problem is that this is infeasible to train from SGD, the stochastic gradient descent, which we need to use to train a deep neural network model. Okay, so the reason is that for SGD, we require each component to be independent. But here, this term requires us to sum of all the neighbors, which means we are not able to do link by link to throw into SGD, because each link considers all the neighbors over there. Okay? And so our solution is like to use a simple Corsi-Schwarz inequality. This can be bounded by this particular equation, and this is a sufficient condition for the L here. Means that if we optimize this, you will automatically optimize this L. That's what we want. And the good point for this is like right now we don't have this summation of pi. So this right now, like each individual link is itself. So you have I and J. So you can throw each individual link as a training instance into this neural network and to train it through SGD. So our framework is like that. So each positive link will be regarded as a input, a pair of inputs. So it's a UI and UJ, and throw it into this neural network. Eventually, we get a gradient from the objective and back propagate to tune up the weight, and then we throw the next link into this framework. So it keeps chaining until converge.
Ask a question.
Sure.
So is there necessarily a connection between the ranking and the graph?
Mm-hmm. The connection, you mean?
Well, so you just defined in your ranking metric, you had the proximity of two nodes, right, as part of that metric. But it's not the case that you're trying to learn maybe simultaneously a graph topology and an absolute metric that don't have anything to do with each other. They definitely have to have a very tight relationship with each other. Okay.
Yeah. Okay, then I will describe. Please. 10 minutes. Good. Almost there. I'll describe how we did for the experiment. And so, as I mentioned, graph embedding, embedding is an unsupervised test. Then how do we evaluate this kind of unsupervised test? So people generally use this strategy. So they use those embedding for certain application, and then they compare with different embedding algorithms to see which one allows you to get better performance in those applications. Okay, so here we actually consider 3 different applications. The first is learning to rank. Okay, so learning to rank is a very popular challenge in information retrieval. And so here we have this, we are using this graph of span website. So the data set contains a lot of website graph in the graph, the website in the graph, and there are some span ones and non-span ones. And so this test is to rank the non-span nodes higher than the span nodes. And so those are different embedding algorithms. So each embedding algorithm try to come up with an embedding for each website, and then those becomes a training data to throw into, for example, a linear SBN algorithm, and then we can compare which training data sets allows you to get a better performance. Okay, so that's a typical way how people evaluate. And of course, like to have this paper published, you have to make sure the algorithm does better than anybody else. And the second task is the classification and regression. So here, like we use another data set, and it's called like Facebook wall post. Okay, so this data set has 2 different. So Facebook, I believe people know what it is. So they are friends, they are people are friends. So you get a very big graph to connect people through friendship. And in this data set, there are 2 sets of people. One is people they call active set, meaning that they frequently post things. And there are inactive sets, it means that those people don't post very frequently. And so in the classification test, we want to see, we get everybody an embedding. So those different algorithms generate different embeddings, and they throw it to a classification algorithm to see which one allows you to generate a classifier that can separate the active one from the inactive ones better. Okay, so that's the second. The third one is the link prediction. So in this task, so we have a big graph, and we manually remove some of the links, and we are trying to see which embedding algorithm allows us to rediscover those removed links better. Okay, so those are kind of like indirect evaluation, indirect ways to evaluate the embedding algorithm. Okay. So here comes a conclusion. So I will speed up. So I have 2 minutes left. And so no embedding is about deciding what to preserve and how to preserve. And there are several properties that we want to evaluate embedding algorithm. First is scalability. You don't want to suffer this big O n square complexity. So you want to make sure it's linear to the number of nodes or links. And asymmetry, as I mentioned, you want this to be able to take care of the directed link. and unity and simplicity. So one thing I want to highlight here is it's a unsupervised task. You want to get the embedding for each node from the graph itself. So it means that since it's unsupervised, you don't want to have too many parameters. You don't know how to tune. There's no validation data sets. It's not like a supervised task. You can tune the parameters using the validation data. So there's no validation data. So you want to minimize the hyperparameters to make sure, or you want to give a good suggestion for every hyperparameters in your model. Otherwise, people won't be able to get the know how to run it. Okay, so I will skip the other work we were doing, and so we have another work on nudge graph embedding. But I want to really talk a little bit about the future. Okay, so what I believe is like probably it's time to consider both the nudge embedding and graph embedding altogether. So people right now, they are using different strategies to actually tackle these two tasks. And we realize a lot of data sets like Wikipedia or like academic network, they have both properties for graph and for knowledge. Okay, so then a good embedding might need to consider not only the graph properties of those data sets, but also the knowledge property of them. And so to something to combine and prove like a graph embedding algorithm or a Muse, another nudge embedding algorithm could be a cure for this kind of general solutions for this type of data. And another interesting area, I think, is to do embedding even noisy data. But nowadays, we get data that contains noise, a lot of missing links or like incorrect links. And how can we actually make sure the embedding doesn't be affected by those noise in the data? It's a very challenging task. And finally, I want to highlight. So there's a debate. People are talking about whether those kind of embedding should be completely unsupervised, or it should be probably distance supervised or weakly supervised. Because there's an argument, because like every embedding algorithm, there's should be an application attached to it. So it's not doing embedding, that's it. So you should use the embedding for some sort of application. And so in that sense, the embedding should probably be a little bit supervised by considering what kind of task you are trying to do, collect some of the signal from that task, either label data or some knowledge from that task, and use those in your embedding. So that probably allows you to get a better result. Okay, so I want to resort finally to no-free lunch. So it's really similar to people in machine learning. They hypothesis, no, it's not hypothesis, it's a theory. So it's there's no single algorithm that can be performed well in all kinds of tasks. So for embedding, I think it's the same. So it's really hard to find an embedding that's generally applicable to all kinds of different tasks. So in that sense, considering what kind of task, in practice, considering what kind of task you are trying to resolve and use that into your embedding could be a better solution. Okay, so this concludes my talk, and I guess we still have 5 minutes for Q&A. Thank you.
Questions?
Assumption that the graphs together kind of complete and all the edges are there, and when we run Word2Vec, then all the data is there. Maybe there's some typos, but it's all there. But graphs often people forget lengths or
yes, yeah. So you are absolutely right. So like we are right now looking at to remove that assumption. Right now, people are pretty much assume everything is there, but it could be the case like, so our idea is like to perform embedding together with link prediction. We are assuming some missing link are there. So if we jointly resolve these two tasks, try to get an embedding and at the same time try to predict some missing link, then that kind of embedding might be more useful. So that's true. So it could. I don't think it's realistic to assume the graph is complete or there's no noise, and it's meaningful to think about how to deal with that.
Do you think the technique you're developing here can be helpful for word embedding if we assume there are multiple relations between the words? For example, we are not only consider the sequential relation, we also add other type of links, like syntactic dependency, discourse relations, and we treat each word as a node in a graph.
Yeah, that's a very good one. I think people were working on like a sense disambiguation, so they are using WordNet. And so WordNet has different senses, right? And so each sense of the WordNet, they kind of create the embedding. So that's probably similar to use some graph embedding technology on this kind of concept net, WordNet, this kind of knowledge base, and to create embedding. I'm not sure. Other than that, I suppose what you mentioned is like to create your own network or whatever and do embedding.
Yeah, sort of learn word embedding in a graph way.
Yeah, so then the first step is what kind of graph you want to create for. I think there are a bunch of ways to do that, and they could be useful. I think, yeah, it was investigation, I would say. Sure.
I'm still trying to understand what are sort of the main different assumptions, for graph embeddings versus, knowledge embedding. So in the graph embedding case, I guess all the nodes have to be of the same type, and the edges are unlabeled.
Yes.
While in the knowledge embeddings case, you have a graph, but the nodes are of different types, and you have labels on the edges.
Yes.
And so conceivably, you could, so there would be ways of representing that as a bunch of unlabeled graphs, for example. So you could have a graph for each different type of relationship. Or you could, stick all the information into the nodes. You could have unlabeled edges, and so there's actually there's structural ways of doing that.
To answer that, I would probably say existing techniques for graph embedding, they don't care that much about the relation. So it's more like how to preserve the graph structure. And for the knowledge embedding, the relation is very important. So they really don't care about the graph structure. They care about what kind of relation are there between these two nodes. So I think people are looking at different things. Yeah, but as to like decomposing a more complicated graph into multiple simpler one, I think that's doable. But then how? I suppose you mean like each simpler graph you get
you would lose some
embedding.
information.
Yeah.
But I mean, it's all in the. So you would get, say, maybe separate embeddings for each relation type.
Something like that.
You would have to have some way of combining.
Yeah. Anything else?
All right.
Okay,
Well,
thank you.
very much.
So the slides, if you want it, just email me. I can.
Actually, what is still lunch with people?
Yeah, lunch. Do you want to join?
Well,